Good morning, everyone. Let's start. So let's first quickly review what we have discussed in the last lecture. On Tuesday, we'll talk about the least mean square method, right? And that is mainly for training a linear regression model. So regression means that, okay, given, say, n features, I want to predict a continuous value, right? That could be, say, temperature, price, mileage, all kinds of stuff, right? So the model of linear regression actually assumes that, okay, your output is a linear combination of your input features plus some bias parameter. Okay? So here we can, for simplicity, we can represent the model prediction by this W transpose Xi. Remember, Xi contains some constant feature 1, right? The corresponding weight will be the bias, right? So this is a way to simplify the notation. And then to learn the model parameters, namely W here, we use the so-called mean square, we call square loss, right? So basically we use our model to make prediction for every training example. We take the square of error, we add them together. And here we multiply with a constant factor half. It's just to, convenient when we calculate the gradient, you got power 2, and you're gonna have it cancel with this half. Right? That's the only reason we put half here, right? So we introduced the two commonly used strategies to learn or to optimize is this mean square error, summation of square error objective function, right? One is the so-called gradient descent, right? The idea is that, okay, we're gonna initialize our weight vector, then for each iteration, we'll compute the gradient of the square loss with respect to our model parameters. Then we'll update model parameters toward the opposite direction of the gradient, right? And here we have some hyperparameter R, which is called learning rate, right, or step size. So it can be showing that as long as you choose appropriate learning rate R here, this gradient descent will guarantee to converge to the local, to the global minimum of this least mean square objective function, right? And this is the formula about how to compute the gradient, right? This is actually the compute the gradient for every element, with element J, right? So, but there's some problem of this gradient descent framework. That is, every time when we compute exact gradient, we need to go over all the training examples, right? So if you have a huge number of training examples, like even calculating the gradient for once, it will be very, very expensive, right? So that's why people further come out with ideas called stochastic gradient descent. So the idea is that, okay, I mean, the intuition is that people observe that, okay, every time if I want to perform standard gradient descent, I need to go over all training examples to get one gradient, right? Why not just go over one example or two example, and I just add up this product and to use it as approximation of my gradient. I use that approximate gradient to update, right? This is called stochastic gradient, right? So this idea seems crazy, but it has strong theoretical guarantees. So here is the stochastic gradient descent framework, right? Every time, in every iteration, we're gonna pass through every training example, right? For every training example, we just pretend this single example forms the entire training set, then calculate the loss over that single example. I use the gradient to update, right? And this gradient is called stochastic gradient because it's just some random estimate of the true gradient, right? So the theory tells us that as long as your stochastic gradient is unbiased, meaning that if you take expectation over this random gradient, it is the same as the true gradient, then it will converge to the local minimum of your objective function with probability 1, right? So we're not going to talk deep about the theory. Just want to give you a sense that although this algorithm looks very naive or simple, it has strong theoretical guarantees. Okay, so the summary of linear regression as follows, right? So the goal is to predict a real valued output using a feature representation of the input. The key assumption is that output is a linear function of the inputs, right? And we can learn those model parameters by minimizing a total cost. Right? That's basically what we need to know about linear regression. So any questions so far? Okay. Let me. Okay. So we'll finish up the introduction of linear models for regression. Right? Next, we're gonna transit our focus to classification, because classification takes a much more content than regression case. Right? So we're gonna introduce several different learning algorithms for linear classifiers. Right? And we're gonna start with the simplest one, which is called perceptron algorithm. Oops. Okay. So here is our plan. Mm-hmm. Oh, that's weird. Oh. It's a problem. Okay. Oh, that's bad. That's bad. Hmm. Please bear with me for a few minutes. Yeah, let me reconnect it. Okay. Okay. Okay, let us continue, right? So our plan is as follows. So we're going to first introduce the algorithm steps of perception. You see that it's really, really straightforward. Then we're going to do some analysis about the behavior of perception. That will come to the so-called perception mistake bound. And then finally, we'll talk about in practice. I mean, the original perception may not be sufficient, right? We're going to introduce several variants of perception. Right? Those are the how we really use perception in real-world applications. Okay, so let us first recall the definition of linear classifiers. So here we assume we're doing binary classification. That means the output label is either -1 or 1. And the input is an n-dimensional vector x. So linear classifiers use the following rule for classification, right? So we're going to first compute a classification score. This score is just some feature weight vector W transpose x plus b, right? And if you write it out, right, it's b plus a linear combination of every feature value, right? And then you just look at the sign of your score. If it's non-negative, then you predict the label as 1. Otherwise, you predict label as -1. Okay. And this structure is also called linear threshold units. Okay. So this term comes from the neural network literature, because for neural network people, they will everything is a special neural network. That's why they call this linear threshold units. Right? So the good thing is that they come out a nice graphical representation of a linear classifier. Right? So first, we can represent each feature as a node. So for example, I got 8 features, I got 8 nodes, right? And I got a constant feature 1, that is to incorporate the bias parameter. And then we're gonna aggregate those feature information into some intermediate node, right? How can we do that? We connect every feature as well as this constant feature to this intermediate node. The attached to each edge is a weight. Right? You can view that, okay, all those weights on the edges are actually the model parameters, right? So it means that I'm gonna amplify the incoming feature by the weight on the edge, and then send it to the ending node, right? So that means, this basically means, okay, I'm gonna pass this node to the intermediate node by W1 times X1, right? Pass W2, X2 to this node, pass W3, X3 to this node, and eventually pass B times 1 to this node, right? And once we have all those incoming messages arrived, we apply the summation operation in this node. And then the output of this node actually gives the classification score, right? This is actually essentially doing W transpose X plus B, right? This is just a graphical representation how we compute this classification score. Okay. And next, this node will send the score to the next node, right? And this next node will apply a sign function over that, and the sign function tells us how we're gonna give the final prediction. That's it. Right? This is like a simple graphical illustration about how we conduct linear classification. And we just want to give you some sense of doing that, because later we're going to talk about neural networks, right? So they use pretty much the same graphical illustration to describe how the features and the model parameters are combined and compute and propagate throughout different layers. Okay. And also we need to be aware of the geometry of linear classifiers. Right? So basically, for any linear classifier, right, given there are model parameters, like including the feature weights and bias parameter, we can construct a classification boundary. Right? So the classification boundary partition the instance space into 2 half spaces. Right? On one side, all the examples are classified as positive. On the other side, all the examples are classified as negative. And this boundary can be analytically represented by this equation. That is the classification score A0. Right? So if you can recall what you have learned in our high school, a linear equation equals to 0. A linear equation, right, actually is represented by a line or plane or hyperplane, right? That's why we call it hyperplane. So, and another interesting property is that this actually we have discussed previously. The vector that is orthogonal to this hyperplane is the feature with vector. So in this case, you might think, oh, okay, this is trivial because it's just a line, right? But imagine that in the three-dimensional space, this will be plane. So basically, it means that this plane contains many infinite number of different vectors, right? And this width vector will be orthogonal to arbitrary vector stay on this plane. Okay. Again, like to strengthen your idea or understanding about geometric representation of linear classifiers, I highly suggest everyone try to show that this plane or this hyperplane is orthogonal to this feature weight vector. So it's not hard to prove, but just need you to think about 3 minutes, right? But it will be helpful. And another important thing we need to be aware is that actually, if you just reskew the model parameters, it won't change the classifier at all. Right? If you reskew them by 0.1 or 1 million, it doesn't change the classification boundary at all. It doesn't change the width vector at all. Right? Okay, any questions so far? Everyone is comfortable so far? Okay, so we can see that given a set of training examples, for example, those black examples and red examples, right? The learning of linear classifier essentially is to adjust the weight vector and bias parameter to find the right position of your hyperplane, right? Or classification boundary. That's the learning procedure of linear classifiers, right? So you can imagine when you train a model in this plane, you got some classification boundary kind of dynamically varying, right? Until you find the right position. That's basically the training procedure, right? So the first approach we're going to discuss in training linear classifiers is called perceptron. This is actually a very classical and old method, and the original paper was published in 1958. Right? And there was the paper was written by one pioneer in our domain, whose name is Rosenblatt. Right? And then the so-called perceptron becomes extremely hot in research and even in news media. Right? So this is some old newspapers showing that, okay, looks like the perceptron will show some true intelligence, right? People are going to use that to replace human beings and so on. Right? So it's very like nowadays, people talk about AI, right? And people are thinking about, okay, our large language models or whatever other artificial intelligence algorithms are showing intelligence and so on, right? So it's the same thing happened 70 years ago. But later, people found that the perceptron essentially is just a learning algorithm for linear classifiers. The goal is to find a separating hyperplane of your positive and negative examples, right? And in essence, it's an online algorithm. Basically, you're gonna pass through the training data sequentially, right? And each time it only processes one example. And of course, for practical usage, there are several variants. Okay, now let us look at what is perceptron algorithm. Okay. So we assume our input is a sequence of training examples, so x1, y1, x2, y2, and so on. Right? And we assume that, okay, those feature vectors are in n-dimensional, right? And your label is either -1 or 1. Right? So at the beginning, we're going to initialize our model parameters W0. And here, I want to mention that this W0 contains the bias parameter. So we use this succinct representation. That means all those xi's are have already been augmented with some constant feature 1, right? So we initialize the whole model parameters to 0, right? Then we're gonna sequentially go through every training example. And for the current training example, say xi, yi, we're gonna make a prediction with the current model parameters. Okay. So this is my prediction, say y prime, right? So I'm gonna check if my prediction is correct or not. Right? If my prediction is correct, then we do nothing. We just look at next training example. Otherwise, we're gonna conduct some update. Right? How can I do the update? Right? We're gonna multiply the label, true label y with your feature vector xi times some learning rate r. We add this to the current weight vector. We obtain our updated weight vector. Then we move to the next training example. We just keep doing this, right? We can just pass through the whole training set for once, or we can pass through it many, many times. But every time we just want to stream those training examples to our algorithm. After the processing is done, we return the final weight vector. So this is called this is the original perceptron algorithm. Any questions so far? Everyone is clear about how this algorithm is running? Okay. So here, we just want to emphasize that W transpose X actually has already included the bias term, right? And we have already folded into the weight vector, right? Another thing is that here we assume the label is either -1 or 1, right? But in some other literature, you might say, okay, they assume the label to be 0 or 1, right? But it actually doesn't matter. Right? So, however, if yi is 0, how should we 0 or 1? How should we modify this algorithm accordingly? Any thought? So if you look at the whole algorithm, right? The updating rule is like as follows, right? So we add WT R times YI XI, right? So here we assume YI is either 1 or -1. So now if we switch to 0, 1 representation of Y's, we should modify them accordingly, right? Otherwise, consider if Y is 0, it actually does not do any update, right? So now I want to ask, how do we modify this updating rule accordingly? Can I say it again? Minus R. Yeah, if you're doing some if else rule, you can do that, right? But do we have like some single, just a little bit manipulation of the Y to? So take another term as R or inverse velocity matrix. Yeah. Yeah. I mean, we can definitely do that, right? So meaning that, okay, I can check if yi is 0, then I'm gonna do r times -1 xi, right? But here there's a simple transformation. So if yi can only take 0 and y, 0 and 1, we can replace yi here by 2yi - 1. Okay, so let me write it down to be more clear, because this is a very important trick, right? So, sorry. So when yi can only take 0 and 1, right? Then we're going to change the update rule by replacing yi by 2 yi minus 1, right? So that means, okay, if yi equals to 0, then this factor you multiply with multiply to xi will be minus 1, right? And if y is 1, then this one will be 1, right? So it will be consistent with the case that y can take minus 1, 1. This is very, very often used trick. Just give you a sense. Later we'll come back again. Okay, any other question? Okay. And then let us look at the what happened after we do the updates, right? So first, we notice that the updating only happens when we make a mistake. Right? If we do not make the mistake, we do nothing. Right? It's kind of lazy update. And then if we make a mistake on the positive examples, meaning that your ground truth label should be 1, right? But you happen to predict as negative 1. Then yi equals to 1, then your updating rule will be like this, right? Here. You add WT R times xi because yi is 1. On the other hand, like if you make a mistake on negative example, then your update will be subtracting WT by R times xi. So later we'll talk about why such updating rule makes sense. This is our first observation. Second is that, okay, here R is a learning rate, is a small positive number less than or equal to 1. So the role of R here is similar to the gradient descent or stochastic gradient descent we have previously discussed. And third one, update only on errors. So we can also call this perception learning is a mistake-driven algorithm. Right? If my current weight vector works well, I don't do any update, right? If it makes a mistake in predicting any training example, I'm going to update my model parameters. And this is the simplest version of the perception, right? So later when we talk about the practical variance, we'll see several more robust variants. Right? And the last thing we want to mention is about how do we check if our prediction is correct or not, right? So here we just look at, okay, if your predicted label is consistent with the correct label, right? But there are another commonly used trick. You just check this guy is negative or not. Why is this correct? Right? Why is this the right checking condition? Any thought? What? This is not a loss. Yes, exactly, right? So remember, WT transpose xi is our classification score, right? If it is consistent with your true label, the sign should be the same, right? So that means their product must be positive or non-negative. You can see, okay, you make a correct prediction. Right? If their signs are different, then their product must be negative. And their signs are different, meaning that the prediction is wrong. Right? So this is a very, very common used trick. Right? So we'll reuse it in some elsewhere, right? So just keep it in mind. Right? Okay. So now let us talk about why such a heuristic rule in updating our weight vector is reasonable. Right? Why should we impose such a updating rule? Right? Let us consider when we make a mistake on a positive example. Right? That means the true label is 1, right? But our classification score is negative. So we can see that the reason we make a mistake is that our score is too small, such that it is below 0. If we want to update our model, right? I want to correct this mistake. How can we do that? We should change our model parameters such that the new classification score get increased, right? And in the best case will be bigger than 0. Then we can fully correct our mistake, right? That's the idea, right? Like, for example, if your if your true label is 1, but my classification score based on current WT, you say is negative 0.5, right? If I want to update my weight vector, right? I want to update that so that your newly updated weight vector, when you use it to compute classification score, it will increase, right? Say increase it to 1.0, then my score is above 0, then my prediction will be correct. So the way to improve our classifier would be make the classification score to increase, right? Does it make sense? Right. So now let us check if our perception update are doing the right thing, right? So when we make a mistake on the positive example, right? So our new weight vector will be WT plus X. And here we assume the learning rate is just 1, right? So just follow this rule. And then let's check with the newly updated weight vector, how will the classification score change? Right? So the new score will be WT plus 1 transpose X, right? So we know that WT plus 1 is simply WT plus X. Then you do the dot product with X, you just, multiply them into every term, right? So we got WT transpose X plus X transpose X, right? So this is the old score, right? This is score before update. And then we actually add the old score with X transpose X, right? And X transpose X is usually bigger than 0. So you can see that the new score actually got increased value upon the old score, right? So that means it tries to improve the classifier, right? Because the old score is below 0, it's too small, which makes it to be incorrect, right? So now I add some positive value to the old score to get a new score, so it has better chance to get above 0 and correct our mistake. That's the idea, right? But however, that does not necessarily mean that, okay, if you add X transpose X, your new score will be bigger than 0. There won't be such a guarantee. But at least the updating direction is right? I try to lift my classification score. And if I happen to make the new score above 0, I completely correct the mistake. Right? If it's not, maybe next time we'll meet this example again and do this again. Right? And after a few times, I expect that I can completely correct my mistake. Does it make sense? Right? And we can observe or examine the rule when we make a mistake on predicting negative examples. They're doing kind of similar things. Right? So I will leave it as an exercise for you for analysis, right? To help you better understanding the motivation and rationale of this updates. Okay, so far, any question? Everyone's comfortable? Okay. So now we want to give some geometry view about the perception updates to strengthen our understanding about the algorithm behavior. Right? So suppose this is our current weight vector, we denoted by WO. Right? So we mentioned before, right? The weight vector is orthogonal to the classification hyperplane, right? So this is a classification hyperplane. So now, if we use our current model to make a prediction over this positive example, what will happen? What's the label? It'll be incorrect. Yes, it'll be negative. Why? Because if you do W old transpose X, what's the value? It is positive or negative? It's negative, right? Why is negative? Yeah, we asked you to not to assuming this is just a strict two-dimensional plane, right? This will be negative even you have like arbitrary dimensional space. So why is this negative? Why the dot product is negative? What? Yeah, the answer right. Yeah, yeah, but can you put it more like root reason?
You're saying doesn't matter where it's actually in this 2D space, it's still alter space. Except isn't necessarily only in some space.
Yes.
Because so you know X, then you transpose
X is not necessarily negative. X could be a vector, and some elements could be negative, some elements could be positive. But we're gonna still claim that okay, this classification score, meaning the dot product between W old and X, will be negative. Why? Why is this true?
And so just because it's really the opposite direction
of yeah, you're closing to the point, right? But you just need to recall what you have learned our perhaps high school. That's my best memory. Right? Why this inner product is negative. Yeah. So let me repeat, right? The reason this dot product is negative is because the angle between the two vectors is bigger than 90 degree or half pi, right? So everyone, I believe everyone has recalled, right? Right? Because the dot product has the same sign as the cosine, right? Cosine of the angle between the two vectors, right? So if this angle is over half pi, cosine will be negative. That means dot product must be negative. Right? Okay. So if you still feel uncomfortable, I just threw out the equation. I just threw a definition, right? So for any two vectors, u and v, right? I know that in arbitrary dimensional space, they must have some angle between them, right? And if we denote their angle by theta, then what is cosine of theta? Anyone can recite the formula. Yes. This guy is equal to the dot product between u and v divided by the norm of u times norm of v, right? The norm here in Euclidean space means just the length of the vector, right? This is just a formula. This is just a known formula. I believe everyone has learned that before, maybe a long time ago. Right? So this basically tells out, okay, according to this formula, if the angle between two vectors, they're over 90 degree or half pi, the dot product must always be a negative, right? That also explains, okay, on the, I would say, this side of the hyperplane, you always predict the example that's negative. Right? Why? Because every example on the other side, on this side, right, they're gonna have a degree angle over half pi from W, right? On the other hand, like for all the examples right here, on the same side where WO point to, right, their angle with WO will be less than 90 degrees. So dot product will be positive. So that's why they always predict those examples on this side as a positive. Does it make sense? Right. So yeah, if you feel uncomfortable, just check this. Check out this formula. Check this is just definition cosine theta. How you can kind of compute the cosine of the angle between two vectors. You'll know that. Okay. So now we know that. Okay, given the current model, right, we're gonna make a mistake on a positive example. And now we're gonna update our model parameters using this rule, right? This is perception rule. How can I do that? So here we assume R is 1, right? That means our updating rule will be adding W to X, right? Because R is 1, right? To get new W, right? Let's see if we add X to W, what will our hyperplane, classification hyperplane change, right? So geometrically, if we want to add one vector here, right, to another vector, we just move the second vector in parallel, right? You make the end of the second vector to overlap with, starting of the second vector to overlap with the first vector, right? Now you just connect the starting of the first vector to the end of second vector. That's our new with vector. Does it make sense? And accordingly, because this is our new with vector, our hyperplane, our classification boundary will be orthogonal to the with vector. So this is where our new classification boundary stays. So now, what is our prediction on X? Greater than 0. And then what is the label we're going to predict? Positive, right? So now that means, okay, after such update, we can correctly predict this example, right? We correct our mistakes. Any question? Okay, so let us use another example to show if you make a mistake on an active example, what will happen. Suppose this is our current model, right? This is our with vector, this is our classification hyperplane, right? Now I have a negative example here. If we use our current model to predict X, what is the label? Positive, right? Why? Because the angle between the example I want to predict and our model with vector is less than 90 degrees. So the dot product will be positive. So I'm gonna, my model will predict as a X as a positive, right? But this is not true, right? Because true label is negative 1. So we make a mistake on an active example. Right? And then we're gonna apply the rule as we just mentioned, right? This rule, the second rule. We made a mistake on active. We're gonna subtract our current weight vector by xi times the learning rate r, right? And again, we're gonna assume r equals to 1, right? So then our updating will be subtract current w by x. So in geometry, if you want to subtract w by x, how can we do that? Does anyone recall how to do that? We should be good of doing this during our high school, right? Yes, right? You just w minus x equals to w plus minus x, right? So minus means that you just reverse the direction. Right? So you're gonna basically we're gonna reverse the direction of x, right? Like this, right? And then you just move it in parallel such that your starting point collapse with the ending point of W, right? Now you connect this guy and this guy, you form the updated weight vector, right? So this is our updated weight vector, and accordingly, our classification boundary will be perpendicular to W nu, right? This is so that's why our classification boundary sticks here, right? So now, if we use our new model to make prediction on X, what's the label? Negative, right? Why? Because this angle now is bigger than 90 degrees, right? So dot product is negative. So our prediction will be negative. Now, your prediction is right, right? Okay. So far, any question? Okay. So hopefully our analytical analysis and also geometric analysis can give you some sense about the rationality of the perception learning algorithm. So the next question we want to talk about is the learnability of perception. Right? So obviously perception is trying to adjust the position of a hyperplane to well classify a data set, right? But what if this data set is not linearly separable? Will perception converge or not? Or if this data is linearly separable, meaning that, okay, there are a group of positive examples, there are a group of negative examples, we can draw a line or hyperplane to well separate them out, right? If in that case, will perception converge? So this is something we want to discuss, right? So first, perception cannot learn what it cannot represent, right? So it can only well learn the linearly separable functions. You see that when your data set is linearly separable, it will converge in a finite number of steps, meaning that in a finite number of steps, it won't make any mistakes in going through the whole data set. So it can stop, right? But when your data set is not linearly separable, and it will just enter into an infinite loop. Okay. So Marominsky and Papert in 1969 wrote an influential book, okay, and they're talking about the limitation of linear classifiers. Right? Perception, of course, is one instance of a linear classifier learning algorithm. So in that book, they proposed the so-called parity function and show that parity function cannot be represented by linear classifiers, so that can be learned by perceptions. But later, people found that we have some feature transformation trick, like I mentioned before. If we can smartly transform the feature and map them into a higher dimensional space, we might still find a hyperplane to well separate positive and negative examples, right? That means in a new feature space, we might still be able to run perception and converge in a finite number of steps. Okay, so now the second problem we want to discuss is the behavior of perception learning algorithm. We call it perception misty bound. So first, convergence. We have a so-called convergence theorem for perception algorithm. Specifically, if there exists a set of weights that are consistent with the data, meaning that, okay, I can find there exists a linear classifier or hyperplane which can perfectly separate all the positive examples from negative examples, then you run perception algorithm, it will converge. And it does not necessarily converge to the hyperplane we mentioned, right? But it will eventually converge. And we have a second theorem about perception. It's called cycling theorem. What it says is that, okay, if your training data is not linearly separable, that means you cannot find any hyperplane that can separate all the positive examples from all the negative examples. Then if you keep running perceptron algorithm, it will eventually repeat the same set of weights and enter an infinite loop. So like you got W1, W2, W3, W4, and just your update is just cycling around this set of distinct weights. So this is the basic behavior of perceptron channel.
So it doesn't necessarily stop running like
Yes. 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 Here we are assuming that okay, we're going to repeatedly stream the whole training data to perceptron. Right? Only when it doesn't make any mistakes over the whole data set, we stop, right? And in convergence theorem tells that okay, if your data set is linear separable, well, after a finite number of updates, it will correctly predict every training example, it will stop. And for cycling theorem tells us, okay, if your training data is not linear separable, that means it will just run your perceptron forever and ever. Okay, any other question regarding the understanding of the theorems? No, it doesn't depend on R. You mean the learning rate, right? No, it doesn't depend. Yeah, we'll run into the proof of theorem, so we can have a better understanding of the insight. Right? But before that, we should figure out. We should be sure that we all understand what does these two theorems. What do these two theorems say? Right? No question. Okay. So we're now going to prove the second theorem. Just to tell you, okay, if your data set is not linearly separable, if you keep running that, it will not stop. What we're mainly focus is show that convergence theorem. It actually reflects the behavior of perception. So before we talk about the convergence theorem, let us first introduce several important concepts. Right? So first, the concept is called margin. What does margin mean? The margin is talking about a data set and a separable hyperplane. So if a hyperplane can linearly separate a data set, then this hyperplane has a margin for that data set. Right? If that hyperplane cannot do that, then we should not talk about margin. Right? So what's the definition of margin? Right? It is the distance between the hyperplane and the data point which is nearest to the hyperplane. Okay. So let us look at the example here. Right? So we got a bunch of positive and negative examples. Right? For a separating hyperplane, this blue line, right? The margin actually is the distance between the hyperplane and the point in this data set which is nearest to that. So basically, you can calculate margin by calculate the minimum distance between every data point and the hyperplane. So this is the definition of margin, right? So just be careful, like margin is defined between a hyperplane and a data set. And the precondition is that, okay, this particular hyperplane can well separate all the examples in that data set. If it does not separate this data set, it doesn't have any margin. And we can further generalize this idea, right? Extend this concept to the so-called margin of a data set. That will become some internal property of the data set. So what's the definition for the margin of a data set? So first, we're going to assume that if this data set is linearly separable, then the margin of this data set is the maximum margin possible for that data set using any weight vector. The meaning is that, okay, I'm going to look at all possible separating hyperplane. Right? For each separating hyperplane, it has a margin for this data set, right? and I pick up the one who has the largest margin. And then I use this margin as the margin for the whole data set. If you look at this data set again, right? Positive and negative examples, we know that there can be infinite many different hyperplanes that can well separate positive and negative examples, right? And each hyperplane might have different margin, right? And then I'm interested in looking at which hyperplane has the largest margin. It turns out to be this blue line, right? And this largest margin, we take it as the margin of the data set. No, there's no guarantee that you can solve it analytically. Yeah. Because for those for many like linearly separable data set, right? You have like infinite many hyperplanes, right? You just define that, okay, I'm pick up the hyperplane that gives the largest margin as the margin of data set. Right? It's an internal or intrinsic property of data set, right? And this intrinsic properties of data set reflects how separable the data set is, right? So this is a very important idea, right? That's very important inside our data set. So if your margin is large, that means the positive examples are generally far away from negative examples, right? If your margin of the data set is small, that means, okay, the positive and negative examples are closer. And this separability actually reflects the easiness of this data set, right? Remember, if the data set like the clusters positive and negative examples are very further apart, you can imagine, okay, my training will be pretty easy, right? However, if your two clusters of examples like are very close to each other, your training will be much more challenging. Does it make sense? And the question regarding the definition of margin, right? Because this is a very, very important concept. We're gonna look at this again when we talk about support vector machines. That's why I want everyone to be feel comfortable and to be clear about that. Okay, great. And the second thing we want to review is the definition of distance. So I'm sure that you guys have already learned this equation maybe a long time ago, right? But here I just drop them here again, right? For a reference, right? So generally, we can use such a linear equation to represent a hyperplane, right? So W transpose X plus B and S can be in arbitrary dimensional space, right? And now, if I in the same input space, I want to compute the distance between arbitrary point x0 and h, right? So this is a hyperplane. This is x0, right? If I want to compute the distance between x0 and h, that means I want to compute the length of this this guy, right? So the formula is as follows. We just evaluate the left-hand side of this equation at x0, take the actual value, then divided by the norm of the weight vector W. Again, if you're interested, you can try to prove this. The proof is not hard. I just ask you to recall your memory long time ago, right? If we are doing this in augmented feature space, that means I'm gonna insert a constant feature value into X, right? So then my bias parameter has already been folded into X, right? Then my hyperplane will be W transpose X equals to 0, right? And similarly, if I got my point x0 in the augmented feature space, if I want to compute the distance, you just use this formula, right? We take the absolute value of the evaluation of left-hand side at x0 and divide it by norm of W. And remember, in our case, we're going to use W, this hyperplane, to do the classification, right? If your hyperplane can correctly predict the label of x0. Then I can replace the numerator by y0 times w transpose x0. Why? Why I can replace my numerator by y0 w transpose x0 rather than take an absolute value of w transpose x0. Yes, right? So remember, this is just the absolute value, right? So no matter your score is positive or negative, right? If you make correct prediction, when you multiply y0, it will be the absolute value of the w transpose 0 because this guy will give you a positive number, right? Y0 is 1 or minus 1. Okay, so now let us talk about the so-called mystic bound theorem. It's a very well-known theoretical result about perceptual learning. So let x1, y1, x2, y2 until xm, ym be a sequence of training examples, okay, such that for every training example, the feature vector xi is in the n-dimensional space, and the norm of xi is upper bounded by r. So this basically says, okay, the length of each feature vector is less than or equal to r. And we assume the label is either -1 or 1. And then suppose this data set is linearly separable, right? Meaning that there exists a unit vector u. Unit vector means that the norm or length is simply 1, such that there is some positive gamma. And for every training example, xi, yi, we have this yi times u transpose xi no less than gamma. So the second precondition. Then we run our perceptron algorithm. The perceptron algorithm will make at most big R over gamma square mistakes on the training sequence, and then it can stop. So R, big R here is the maximum length of the training feature vectors, right? And gamma here exists in the second condition, right? We'll talk about what does gamma exactly mean. And then conclusion is that, okay, the perceptron algorithm will make a finite number of mistakes. And then it can correctly predict every training example and stop. Right? And we can give an upper bound of these mistakes or updates the perceptron algorithm can make, which is R over gamma squared. Okay, so now let us look into more closely to this theorem, right? So first, we're going to assume that all the feature vectors have already been augmented with constant 1, right? And then a very important precondition is that we assume your feature vector, the length is upper bounded by some r, right? This is actually relatively easy to find, right? We can always find such r. We just look at which data point is furthest from the origin. Right? Now, the interesting things come from the second precondition. So the second precondition says that, okay, we have a separating hyperplane U, right? But U has the norm to be 1. Then, and for every training example, we have this yi times u transpose xi and no less than gamma. What does gamma mean? If we take a look at left-hand side, if we divide it by the norm of u, what does it mean? if we divide the left-hand side by the norm of U, what does this guy mean? Yeah, someone says it's distance, right? It's just we have just reviewed, right? The distance is here, right? And remember, because it can predict every training example, so you can replace this absolute value by the label multiplying with the classification score, right? So if you're going back, right? So you can see that label multiply the classification score divided by norm of U is distance, right? And because U is a unit vector, so the norm is simply 1. Right? So that means the left-hand side essentially is the distance between every training example xi, yi, and the separating hyperplane, right? And then it means that okay, the distance between every training example and the separating hyperplane determined by U is no less than gamma. What does gamma mean? The margin, right? So the margin is the minimum distance between the data points and the hyperplane, right? So if you say, okay, that means the margin, that means the distance between every training example should be no less than the margin, right? So actually gamma provides the margin information for this separating hyperplane view on the training set. But here, one would like to ask, okay, what if I do not assume U is a unit vector, right? If U is not unit vector, then the bound won't be like this. You have to shove the norm of U into the bound. Right? But here, for convenience, let us assume U has already been normalized, meaning that their norm is U, right? Then we can see that the number of mistakes the perceptron make during their training will be at most the largest length of the training vector divided by some margin of separating hyperplane and take square. That's what the Misty-Bound theorem reflects. If we put it in a more concise way, the Misty-Bound theorem just tells us that suppose we have a binary classification data set with n-dimensional inputs. If the data set is linearly separable, then the perceptron will find a separating hyperplane after making a finite number of mistakes. Remember, finite number of mistakes. After making each mistake, the perceptron will update once, right? So it basically means the perceptron algorithm will find a separating hyperplane after doing a finite number of updates. That is what the Misty-Bound theorem tells us. So any question regarding the understanding about this theorem? Everyone's comfortable? Okay, so next we're going to prove this theorem. So here is the basic setting. In our perceptron, we're going to initialize our weight vector to be 0. For simplicity, let us assume learning rate is simply 1. Right? So we do not care about R. Right? And first precondition, all the training examples are contained in a ball of size R. So meaning that the length of each input vector is less than or equal to R. Right? So you can imagine that this is your training input, right? They are all contained in a ball with size R, with a radius R. Right? And the second precondition is that the training data is separable by a unit weight vector U with margin gamma. Right? This basically tells us that, okay, the distance between every training example and the separating hyperplane determined by U is no less than gamma. These are two preconditions. So now let's try to show the Misty bound. Right? So there are 3 steps. So we're going to use induction to show 2 inequalities. Right? Then in the 3rd step, we're going to connect them together, and we can derive a bound for the number of mistakes we made. So the first step, we're going to show an inequality that after t mistakes or t bound t updates, we always have u transpose wt is no less than t times gamma. So basically, wt means that okay, after t updates or t mistakes, what is our current weight vector, right? If we calculate dot product between u and wt, it will be lower bounded by t times the margin of u for the data set. So how can we show that? We use induction. Let us assume that, okay, at step t, this inequality holds. We just want to check, can we extrapolate this same conclusion to t plus 1, right? If we look at u transpose wt plus 1, because at step t, right, we made mistakes, right? So according to the updating rule, wt plus 1 will be wt plus here, right? yi times xi, right? And then you do the inner product between u and the updated weight vector. You can represent it as u transpose wt plus yi u transpose xi, right? So because u is a separating hyperplane, right, with margin gamma, so this guy, this additional term essentially is the distance, right? So this distance, we know that it is no less than gamma, right? And the u transpose wt, according to the induction assumption, has already satisfied this guy, right? So if you put them all together, you got this t gamma, right? You add one more gamma, you got u transpose w t plus 1 is no less than t plus 1 times gamma, right? So the induction step is relatively straightforward. As long as at step t, this holds, then at step t plus 1, it holds as well. Right? And next, we're going to check at the beginning if this inequality is correct. Right? At the beginning, we know that W0 is 0, right? Because we initialize all the weights to be 0, right? Then u transpose W0 is simply 0, right? And t is 0 because we haven't yet making any mistakes. So 0. So 0 is no less than 0. So at the beginning, it's correct. Then according to those induction steps, it can extrapolate to up to t. Does it make sense? Right? I mean, it's just the standard induction framework for proof, right? And you just leverage the results, leverage the preconditions, right? This guy, right? And you can, from each step, to show the next step is correct. And at the beginning it is correct, then you can follow the same logic to show it applies to every possible t. Any questions so far? I mean, if you feel uncomfortable about that, after class, just go through this proof. It won't be hard. It will just take you a few minutes. Okay, so we show the first claim, right? U transpose WT is no less than T gamma for every possible T. And the second claim is another inequality. We want to show that for any T, meaning that after T mistakes, the square norm of our current weight vector WT is upper bounded by T times R squared. So here big R means the upper bound of the length of the input vectors, right? This is our precondition, right? How can we show that? It's still based on induction. Let us assume at step T, this inequality is correct. Right? We want to extrapolate to the step T plus 1. So T plus 1, according to the updating rule, right? WT plus 1 will be WT plus YI xi, right? You just look at the square norm of this WT plus YI XI. And this guy you can expand, right? You can expand this quadratic term, right? You actually have three terms: the square norm of WT, the square norm of YI XI. Right? Y is either 1 or -1, so it doesn't change the norm. So you got the second term, right? And third term is the cross term, 2 YI WT transpose XI. Okay. So first, according to our first precondition, we know that XI is square norm of XI is less than or equal to R, right? Second, for this one, according to the induction assumption, this guy will be less than or equal to TR square, right? So you can see that adding this one and adding this one, we have already add T plus 1 R squared, right? Right? This is R squared. Right? So we can take a look at the middle term. So I want to ask, is the middle term positive or negative? It's negative. Why? Yeah, because you make a mistake. You make a mistake in current update, right? So at mistake T plus 1, meaning that, okay, you make a wrong prediction at this part, right? So that means this guy must be negative, right? So you can see that the norm of the square norm of WT plus 1 will literally be smaller than this guy plus this guy, right? Because it actually add an additional negative term, right? Then we immediately show the induction is correct, right? So it will be less than or equal to T plus 1 R squared. Okay. And the remaining is just to show at very first step it's correct. Right? And it's relatively easy because when T is 0, we know that W0 is 0, right? WT is 0, and T is 0, and right hand side 0. Let 0 less than or equal to 0. And then following the same logic, you can extrapolate to arbitrary T. Right? So we finish step 2, right? Again, if you feel uncomfortable or didn't catch up, doesn't matter, right? Just after class, you go through the slides again. I won't take you too much time, right? So after the first 2 steps, we have shown 2 inequalities. First, after T mistakes, we got U transpose WT is no less than T times gamma. After T mistakes, we got the square norm of the weight vector upper bounded by T times R squared. Right? The third step will just to link these 2 inequalities together. Then you get some upper bound of T. So from 2, right, if you reverse the direction and take the square root on both sides, right, you get R times square root of T, right? You take square root of this side, right? And is no less than the norm of WT. Then if we apply the so-called Cauchy-Squarz inequality, you can get norm of WT is no less than U transpose WT. And now you can link to the first inequality you get, right? Sorry. You get U transpose WT is no less than T times gamma, right? So now you just connect the right end and the left end. You just solve that inequality. You get number of mistakes is no less than R squared or gamma squared. Right? That's how we show that. Right? And regarding Cauchy-Squarz inequality, it's just based upon the definition about cosine, right? So U transpose WT equals to norm of U times norm of WT times cosine of their angle, right? Because the cosine, its value is always less than or equal to 1, right? So that basically means the dot product is less than or equal to the product of their norm, right? And further, because U, the norm is 1, it basically means U transpose WT is less than or equal to the norm of WT, right? That's how we get here. Right? Okay, so let's stop here today, and we're gonna after our fall break, we're gonna just review this proof again. Right? And hope everyone enjoys a great fall break. And don't forget to start your homework 1 or homework 2.